Okay, so today we're going to look at power series. So, power series. Okay, so we spent quite a bit of time talking about series, obviously. It's been pretty much the whole class. And we've looked a lot at convergence, divergence. Most of the time that's what we've been spent is whether or not a series converges. So we want to look at some specific kinds of series and eventually reach the point where we can talk about application of series. So in this section on power series, we're going to start by saying a power series about A or you can just say a power series is any series that can be written in the form the summation from 0 to infinity of c of n of x minus a to the nth power, where a and c of n are numbers. The c of n's are often called the coefficients of the series. So the c of n is often called the coefficient of the series. The first thing we notice about a power series that it is a function of x. That is different from other series that we've looked at to this point. In all the prior sections, we've only allowed numbers in the series, and now we are allowing variables to be in the series as well. This will not change how things work. Everything that we know about series is still true. So in the discussion of power series convergent is still a major question that we'll be dealing with. The difference is that the convergence of the series will now depend upon the values of x that we put into the series. A power series may converge for some values of x, but not for the other values of x. Before we get too far into it, I want us to look at some terminology. So first, as we will see in our examples, we will be able to show that there is a number r so that the power series will converge for the absolute value of x minus a is less than r, and it will diverge when the absolute value is greater than r. So this is called an interval convergence. So I want us to look. What I'm saying is if the absolute value of x minus a is less than r, that is the same as having your x between a minus r and a plus r, and that is the power series converges. Okay, then we said when the absolute value of x minus a is greater than r, so that's telling me that my x is less than a minus r, and x is greater than a plus r, then the power series diverges. Okay. And so that's called interval convergence. The interval of convergence must then contain the interval of a minus r less than x is less than a plus r, since we know that the power series will converge for these values. We also know that the interval convergence can't contain x's in the range x less than a minus r and x greater than a plus r, because then it would diverge. So, one last thing before we get into some examples. Let's take a quick look at the convergence of a power series for when x equals a. So, when x equals a, we would have our power series a minus a to the n. And so we know what is a minus a, 0. And so then if we want to pull out the c sub n 0 to the 0, then we would start our n at 1, and we would go from 1 to infinity. And so that would equal, hold on, this should be c of o, because this is the 0 term. So 0 to the 0 is 1. By definition, anything to the 0 power is 1. So that's c sub 0 plus of 0, which is equal, we could put that here, equal to c sub o of 0, c sub 0. Okay? And if, hopefully we all see that connection, but if not, 0 to any power other than 0 is going to give you 0 here. So that's how this is going to be 0, which is c sub 0. Okay, so the power series converges, and we stripped out the first term since it was the only non-zero term. It's important to note that no matter what else is happening in the power series, we are guaranteed to get convergence when x is equal to a. This series may not converge at any other value, but it's always going to converge when x equals a. So, always converges when x equals a. So let's look at some examples. So example 1, we have, let's determine the radius of convergence. The radius of convergence and interval of convergence for the following series. And this is really going to be the directions for every of the examples we're doing today, so I'm probably not going to keep writing that unless I change what we're doing. So let's look at example 1. We have n equals 1 to infinity of -1 to the n times n over 4 to the nth power multiplied by x plus 3 to the nth. So we know that this power series will converge when x is equal to what? So we go up here, and when x is equal to a, well, what is a? A is currently -3. So we know it converges when x is -3. So I'm going to put that side note. X equals -3 means it converges. So we know that. But that's it at this point. That's all we really know. So to determine the remainder of x's for which it converges, we can use any of the tests that we've discussed. So we look here, and we want to find the radius of a convergence. And with this said, the best test to use here are almost always the ratio or the root test. Most of the power series that we're looking at are set up for one or the other. So in this case, we're going to use the ratio test. So if we want to use the ratio test, we're going to say, I'm going to put a little note here. Let's use ratio test. Let's use the ratio test. So L equals the limit as n approaches infinity. We would have a negative 1 to the n plus 1 over, hold on, there's going to be a lot more than that, but over to the 4 to the n plus 1 times n plus 1, and then times x plus 3 to the n plus 1, multiplied by, and then we just flip our original. So that's going to be 4 to the nth over negative 1 to the n times n times x plus 3 to the n. Okay. So we're going to do a lot of simplifying here. And what I can note is I know with this, this and this, that's going to leave the 4n to the n will cancel, and that'll leave us with a 4. And then the negative 1 to the n will cancel, and that'll leave us with negative 1 to the first power, which is a negative. And then, I guess which would be in the numerator. Hold on, let's see. Okay. So yeah, that would leave me a negative in the numerator when I'm looking at those. I will do that in a different color. So I'm looking at this with this, and then that'll leave me this negative. Okay, then our x plus 3 to the n, those would cancel. So that would leave me with x plus 3 to the first in the numerator. Then we also have the n plus 1 that doesn't have anything to go with, and then this n right here. So I need to write the limit here. I think I've told you guys before, but I get to go in and then I forget my notation, which is not a good practice. So the limit as n approaches infinity. So before going any further with the limit, let's notice that since x is not dependent on the limit, it can be factored out. So that means we will have, that's equal to, we can take out the x plus 3, but we need to keep the absolute value because there could be values, that would make it negative. And then we would have the limit as n approaches infinity. So when we take the absolute value, the negative would go away, and we would have n plus 1 over 4n. And so then that limit here, when I take the limit, that would become 1/4. So the 1/4 times the absolute value of x plus 3. So the ratio test tells us that if L is less than 1, if the limit is less than 1, it will converge. And if the limit is greater than 1, it will diverge. And if L is 1, we don't know what happens. So what I'm saying is, going back, I don't have it written here, but that's the rule of the ratio test. So we want to look at, when is it less than 1? When is it greater than 1? So when is L less than 1 and L greater than 1, or where, I guess, would be better. So our limit is this. So when is it less than 1? So it's less than 1 when x plus 3 is less than 4. When the absolute value of x plus 3 is less than 4, because you would multiply by the reciprocal. And then we know, well, when is the limit greater than 1? Well, the limit's greater than 1 when x plus 3 is greater than 4. So this is when the series converges and when it diverges. We'll worry about L equals 1 later. So now we have the radius. The radius is 4. So R equals 4. So now we can go back to what we know. So we know that x plus 3 is between -4 and +4. So x is -4 minus 3, 4 minus 3. So x is between -7 and 1. So most of the interval validity is given by x is between -7 and 1. All we need to do is determine if the power series will converge or diverge at the endpoints. So these values of x will correspond to the value of x and will give L equals 1. The limit is 1. So the way to determine convergence at these points is to simply plug them into the original power series and see if the series converges or diverges using whatever test. So we want to check the series at x equals -7. And so alright, so anyway, checking it at x equals -7. I'm going to change the color. Let's check when x equals -7, we substitute it back into the series. So that was n equals 1 to infinity, and that's -1 to the n times n to the -7 plus 3 to the n, and this part over here was divided by 4 to the n. So, simplifying this, we would look, and that -7 plus 3 is -4 to the n, so we could take that out. We have -1 to the n over 4 to the n. This -7 plus 3 is -4 to the n, which we could write as -1 to the n and 4 to the n. And so, looking here, we can cancel out the 4 to the n's. And that gives us negative 1 to the n times negative 1 to the n, which is negative 1 to the 2n, which is oh, hold on. We lost something. We lost this n. Yeah, I was like, I know this isn't going to just be. So negative 1 to the n and negative 1 to the n is negative 1 to the 2n times n. That's 1 to infinity. And what you should notice here is negative 1 to the 2n. That's negative 1 squared, which becomes positive 1 to the n, which is just going to be positive 1. So this is what we get. The summation from 1 to infinity of n. So this series is divergent if we use the divergence test. So let's see. The divergence test lets us know that the limit is greater than, well, it's not equal to 0. That's because the divergence test has to be 0. Therefore, divergent. Okay, so now we want to look, well, what about the other endpoint? So we want to check it when x is 1. Okay, so now we have n equals 1 to infinity, negative 1 to the n, 4 to the n, times 1 plus 3 to the nth. Okay, so now we can simplify this. We will have negative 1 to the n times n over 4 to the n. That becomes 4 to the n. So our 4 to the n's cancel. And that gives us negative 1 to the n times n. Okay? And so let's look at this. Okay, also we could apply the divergence test and we would see that the limit here does not exist. So I'm also going to use the divergence test. And remember the divergence test, if it doesn't exist, it's divergent. And the only time it's convergent if it equals 0. So the limit of negative 1 to the n times n, and that does not exist, therefore divergent. So in this case, the power series will not converge for either endpoint. So doesn't converge at the endpoints. Therefore, the interval of convergence is x is between negative 7 and 1, but it does not include negative 7 or 1. Okay? So again, this is like putting together a ton of the things we've learned, and you see this problem took, for me, over a page. But again, like I write pretty large with this pen. So now let's look at another example. Example 2. Again, the same the same note, determine the radius of convergence. I'm just not going to write all of that. So we have n equals 1 to infinity, 2 to the n divided by n multiplied by 4x subtract 8 to the n. So in the previous example, the power series didn't converge for either endpoint. Sometimes that happens, but that doesn't always happen. So just keep that in mind. All right, so let's jump right into the ratio test here. So I'm going to write here, we're going to use the ratio test. I know that some of you said you really liked, you thought the ratio test was one of our easier tests, so hopefully you like that. You use that for some of this. So 2 to the n plus 1 over n plus 1, and I'm going to put the 4x minus 8 and then the n plus 1 in the numerator. It'll make it easier, sort of, kind of. I mean, it does. So then you flip the problem you already are given. Okay, so now before we do anything else, like as far as taking away absolute value or anything, we do want to simplify. So the two n's will cancel, and that would leave me with a 2 in my numerator. Also, looking at my numerator, the 4x minus 8 to the n will cancel, and I would just be left with a 4x minus 8. And that n also doesn't have anywhere to go. So I'm going to just put it with the 2 instead of making it more separated. So then in the denominator, we already got rid of all of that. We canceled. So we're just left with n plus 1. Okay, so again, you know, we talked about in the last problem that 4x minus 8 can slide out, but you are going to have to, I'm going to bring my equals up here. You are going to have to keep the absolute value for the 4x minus 8. 4x subtract 8 times the limit as n approaches infinity. And so we took that out, and so we're left with 2n over n plus 1. And so then when you take the limit, 2n over n plus 1, that would become 2 over 1, which is 2. So that would be 2 times the absolute value of 4x subtract 8. So we found our L. And so we want to, you remember in the last problem, we once we found L, we want to know when is L less than 1, when is L greater than 1. So I'm going to do that in a different color. So L is less than 1 when 2 times the absolute value of 4x subtract 8 is less than 1, which would become, hold on, and then L's greater than 1 when 2 times the absolute value of 4x minus 8 is greater than 1. Okay, so we need to be careful here in determining the interval of convergence. The interval of convergence requires that x minus a be less than r, and x minus a, the absolute value of x minus a greater than r. So when we look at this, we don't have it in the correct form because we don't have x minus a. Right now we have 4x minus a, or minus something else. It's not even a. So to get this in the form, we need to divide out a 4 from this. And so to divide out a 4, you would be multiplying the 2 by 4. So that becomes 8 times the absolute value of x minus 2 is less than 1. And the same thing here, if I divide out a 4 in my group, that means I have to multiply that by 4. It's like factoring it out. It's like the opposite of the distributive. Okay, so now that becomes the absolute value of x minus 2 is less than 1/8, and the absolute value of x minus 2 is greater than 1/8. So when it's less than 1/8, this would be converge. When it's x minus 2 is greater than 1/8, that would be where it diverges. Okay, so we want to now note that the radius is 1/8. So r is equal to 1/8. So now we want to find the interval of convergence. So we know that we want to find the interval of convergence. So we solve the inequality. We would have x minus 2 is going to be between negative 1/8 and positive 1/8. So then that tells me x is between, so you would add 2. And so that is adding 16 over 8. So that's 15/8. And 1/8 plus 16 over 8, that gives us 17/8. So now we need to check our endpoints. Check the endpoints. So we want to check 15/8 and 17/8. So we're going to start with the 15/8. When x equals 15/8, all we're doing here is substituting it in to our series. So that's 2 to the n over n. Hold on. Okay, 4. I'm just going to substitute it completely in. That would be 4 times 15/8 minus 8 to the n. Okay, so then that is, we can start simplifying that. 4 times 15 over 8 becomes 15 over 2 minus 8 to the n. So then again, we could have simplified this at one time. So that becomes negative 1/2 to the n. And now if we wanted to pull out the negative 1/2 and raise that to the n, pull out the negative 1. And then in the denominator, you would have n times 2 to the n. And so at this point, you could cancel out your 2 to the n. So the summation, n equals 1 to infinity, that would cancel. We would end up with a negative 1 to the nth divided by n. So this is an alternating harmonic series, and it converges. Therefore, this converges. Okay, so now we want to look at when x is 17/8. So I am going to skip this little part and go straight to the second step. So what I'm saying is I know that 4 times 17 eighths is going to give me 17 halves. And so then simplifying 17 halves minus 8 gives us a positive 1/2 to the n. And we can do a similar thing here where we split up the 1/2 so that then we're able to cancel and have n equals 1 to infinity, 1 to the n over n, which is just because n is going to be positive, it's just going to be 1 over n. Okay, this is a harmonic series and this diverges. This is not alternating. So I'm going to note this was an alternating harmonic. This one was just a harmonic. So one endpoint converges, so that means the 15 eighths is going to be less than or equal to. However, it's not going to include the 17 eighths. So the interval of convergence is this. So, okay. I do want us to look at some special cases. So let's look at example 3. So again, we're going to find the radius of convergence and the interval for a power series. So we're going to go from n equals 0 to infinity, n factorial times 2x plus 1 to the nth. Okay, so we're going to use the ratio test. Ratio test. We have the limit as n approaches infinity. So this would give us n plus 1 factorial, 2x plus 1 to the n plus 1. Oh, yeah. Okay. So divided by, you would flip this so that we're going to divide this by what we have. Okay, we can start simplifying some things. We see the 2x plus 1 to the n's. So what I'm saying is like this, and that part would simplify, but the n plus 1 factorial is not going to go anywhere. So we'd have n plus 1 factorial times 2x plus 1. Right? Yes. Okay. Then you would have n factorial. So we could pull out the n plus 1 and just trust me with why we're going to do this. Remember when you are dealing with a factorial, if n plus 1 factorial would be n plus 1 times n minus 1 times n minus 2 and so on. So if we pull out the n plus 1, that would be times n factorial. And hopefully right this minute you see, okay, I see why she's doing that. So when we do that, I can cancel out the n factorials. And that would allow me, so I'm going to write this. That would become n plus 1 times 2x plus 1. That would, with nothing, no denominator. That just is it. We just canceled out the n factorials. So now, remember, we can take out the 2x plus 1, but you're going to have to leave it inside the absolute value bars, times the limit as n approaches infinity of n plus 1. And then at this point, we need to be careful because the limit is infinite, but there is that term with the x's in front. So our limit would be infinity, which is greater than 1. So what I'm saying here is that this limit is infinity, but it's greater than 1. So provided x doesn't equal negative 1/2. So this power series will only converge if x is 1/2, because right now it's saying your infinity is greater than 1. However, if x was negative 1/2, you'd end up with 0 here. And we don't really know, like we can't say that that's going, we can't really talk about that the same way if x is negative 1/2. So this power series only converges when x equals negative 1/2. So if you think about it, we actually already knew that. From our initial discussion, we know that every power series will converge when x is equal to a. So in this case, a is negative 1/2, because you would have to factor out that 2. Remember, your form is x minus a to the n. So that is 2x plus 1. So that plus would be a minus, and you would have to divide out the 2, factor out the 2, and so that's where the negative 1/2 comes from. So in this case, we say the radius of convergence, your radius of convergence is 0, and the interval of convergence, it's x equals negative 1/2. So that is the interval of convergence, even though it is when x is negative 1/2. Okay, so see, what happened there was our limit was infinity, so that's why we had to then look at when would our limit, though, not be infinity. So our limit's infinity as long as this is a non-zero constant. Yeah. Okay. So lastly, we'll do one more example. I think that might be all that my voice can handle. Example 4. So determine the radius of convergence and the interval. We have n equals 1 to infinity. We have x minus 6 to the nth power, and then n to the nth power. Okay, we want to start here, and I actually think we should use the root test. So, the root test, we still look at the L for our limit, but in this case, we're going to have x minus 6 to the nth and n to the nth, and we're going to raise it to the 1/n. And really, I think this is the best test because both of our numerator and denominator is to the nth power. So when we slide use the root test, we can slide that 1 over n and do some canceling. So the limit as n approaches infinity, we would have x minus 6 over n, not x, over n. And we don't really need parentheses since we have, so what I did was I slid the 1 over n, and so n times 1 over n is 1. N times 1 over n is 1, and here we are. So remember, what we've been doing is we can pull the x minus 6 out, but it has to stay inside of absolute value, and that's times the limit as n approaches infinity of 1 over n. And we know the limit of 1 over n is 0. So 0 times that absolute value is 0. So since the limit, which is 0, is less than 1, regardless of any value of x, it will converge for every x. Since 0 is less than 1 for every x, then the series converges for every x. So we would say our r is infinity, and the interval would be from negative infinity to positive. All right, so I will upload some problems for you to do to go with this.